Now let's see where we actually use proportions in real life. If you were to take anybody who designs things, let's say for example engineers or architects, these folks use proportions when they design buildings, cars, cities, airplanes, and what they do is they build first a model that is in proportion to the original that they're trying to design. And what they do is they just use proportion to scale up their model to the actual thing that they're designing. In this case, an airplane. Okay. Directly into our next section, where we're going to be talking about ratios and similar polygons. So go ahead and take your textbook and turn to Chapter 7, Section 2, and continue to follow along with your notes and write down questions. So let's first go ahead and define what a similar figures are. Similar figures are figures that have the same shape but aren't necessarily the same size. So let's take, for example, these two sets of triangles. We have triangle 1 and triangle 2 right here, and both of these triangles aren't the same size, but they're the same shape. They have angle, angle, angle similarity. Now let's take this example, these two triangles, triangles 1 and triangle 3. These two triangles are not similar. They're not the same shape, nor the same size, so they are not similar to each other. Similar figures are in proportion to each other. So let's dig a little bit more into what that actually means. Specifically, polygons are similar if and only if they meet these two conditions. Number 1, their corresponding angles are congruent. So let's go ahead and define which angles are the corresponding angles and if they are congruent or not. So let's go ahead and start with angle R. We have angle R, and we can see that it's congruent to angle Z right here. All right, let's go back to the first triangle right here. We have angle Q, and we can see that it's congruent to angle Y. All right, then we have the third angle, angle S, and by the third angle theorem, we know that angle S has to be congruent to angle X. Okay, great. So we know that the angles are, there is a set of angles, corresponding angles that are congruent to each other. Now let's see if the corresponding sides are proportional. So how we know which sides are corresponding are, they're the sides that are in between the corresponding angles. So we know that angle R and angle Z are corresponding, and angle Q and angle Y are corresponding. So that means side RQ is corresponding to side ZY. So I can go ahead, what I'm going to do is write a ratio. And we'll see why I'm going to do that in a second. So side RQ to side ZY. And the ratio of the length of RQ to the length of ZY is 3/2. Okay, great. Now what I want to see is, remember, two ratios are proportional when the ratios are equal. So I want to see if the ratio of the two other corresponding sides are equal to 3/2. And if they are, that means the corresponding sides are proportional. So let's go ahead and find the other two sets of corresponding sides. We have QS, which is corresponding to YX, and that is also equal, that ratio is 3/2. So that's proportional to the first set of corresponding sides. And then lastly, we have side, I'll move down here, side SR, the length to the length XZ, and that is also 3/2. Great, so all the corresponding sides are proportional to each other. So we've met the two requirements, check, check, for similar polygons. So that means triangle RQS is similar to triangle ZYX. What I want to do right now is actually write a similarity statement. I'm going to go ahead and erase this. Write a similarity statement that says that exact thing. I will go ahead and write that these are just equal to each other. SR over XC equals 3/2. So they are proportional to each other. So what I want to do now is write the similarity statement, stating that the two triangles are similar. So I'm going to go ahead and write RQS, triangle RQS is similar. This is the symbol for similarity, just this one squiggle, nothing under it or above it. It's similar to triangle ZYX. Now, you might imagine that the order of the letters that I have here is very important as I write the similarity statement. The order tells us something that's very similar to what it told us in a congruent statement between any two polygons, in this case triangles. Angle R is congruent to angle Z, Q to Y, and S to X. So it tells us which angles are corresponding and therefore congruent. It also tells us about the sides. It tells us which sides are corresponding. So RQ is to ZY, QS to YX, and then RS to ZX. Great. So that's important. Now the ratio of the corresponding sides of two similar polygons has a name. It's called the similarity ratio. We just found that the similarity ratio between these corresponding sides is 3/2, which we just found in the previous example. That is if my similarity statement reads triangle RQS is similar to triangle ZYX. Now I can switch the similarity statement and say that triangle ZYX is similar to triangle RQS. But what's going to happen is that it changes my similarity ratio. So since triangle ZYX is now the first triangle in the similarity statement, the corresponding sides of each of the ratios, the numerator is going to be from triangle ZYX. So the numerator is all the sides from triangle ZYX, and the denominator is from the second triangle in the statement from triangle RQS. Okay, so that changes the similarity ratio. It inverts it, and now it is 2/3. So you have to be careful that the order of the similarity statement matters, and it's going to change your similarity ratio depending on the order you write the triangles. Okay. As an example of two polygons that are not similar, let's go ahead and do this particular example. Now remember, the requirements to see if two polygons are similar is number one, see if the corresponding angles are congruent. Okay, so let's go ahead and try to match angles that are congruent between these two polygons. We have angle A, and it is congruent to angle W, so that works. All right, angle B is congruent to angle X. Angle C is congruent to angle Y, and then finally angle D is congruent to angle Z. Great, well, we've met the first requirement. Let's see if it meets the second requirement for similar polygons. That means the corresponding sides are proportional to each other. So I'm going to have side AB. I know that's corresponding to side WX. Well, the ratio 40 to 24 is going to be 5/3. Let's see if the ratio of any other corresponding sides is also 5/3. Let's go ahead and take side CD to side YZ. Well, side CD is 29, length of 29, and side YZ, the length is 18. Well, you can't reduce that fraction, that ratio, so that is what it remains. Well, we know that 5/3 does not equal 29/18. So these two polygons are not similar to each other. The ratios are not proportional. As a last example, let's go ahead and look at two figures that are already similar. We already know they're similar, and let's use the idea of similarity to find a missing dimension between the two objects. Okay, so let's read this problem. In the model Air France plane, so the model right here, the length of the airplane is 1.5 feet, and the wingspan is 0.75 feet. So going to the original, if the length of the original is 320 feet, what is its wingspan? And note, a model is always similar to the original. So we know that the corresponding sides are already proportional. So the lengths of the model to the original are the corresponding sides. So I'm going to say L, the length of the model, to the length of the plane, those are the corresponding sides, are proportional to the wingspan of the model to the wingspan of the plane. Okay, so now I need to plug in what I know. I know the length of the model is 1.5 feet. And I know that the length of the plane of the original is 320 feet. I also know the wingspan of the model is 0.75 feet. But I don't know the wingspan of the plane. That's what we're trying to figure out. So we're going to be able to use the idea of cross products to find the value of x, the wingspan of the plane. So let's go ahead and get our cross products. 1.5x equals 320 times 0.75. So when I reduce that, I get 1.5. I simplify. 1.5x equals 240. And when I isolate the variable x, x equals 160 feet. Great. So we know the wingspan of the plane using similar polygons and proportions. So in review, let's take a look at what we've learned today. Ratios are a comparison of numbers. Here's an example of a ratio, 1 to 2. A proportion are any two ratios that are equal to each other. It's an equation relating those two equal ratios. Two polygons are similar polygons if and only if, under two conditions. One, their corresponding angles are congruent, and their corresponding sides are proportional. Once you've met those two requirements, you can write a similarity statement. In this case, triangle RQS similar to triangle ZYX, and you should be able to find the similarity ratio if they are similar through the ratio of the corresponding sides, right? And when you know that two figures are similar, you can use the idea of proportions to find any missing length of one of the polygons. So if you had any questions while you watch this video, write them down. You should go back to the point that you had a question in the video and watch that part of the video again. Be sure to also bring the questions to class, and we'll discuss them there. Have a great day.